Thank you, Lee, and thank you everyone for taking the trouble to come out on a cold winter's evening like this. I'm going to dive straight in and talk about media coverage, and in particular the tone of outrage when it comes to talking about things like automation, artificial intelligence. You know, the robots we talk about are going to steal our jobs. We're not safe in our beds anymore because of the AI singularity and so on. So really what I'm trying to do here is just look in one small part of that particular forest and dig down deep, and I'm going to compare that, as Lee has just said, really with my experience in the air domain, and try and relate that to things that are probably closer to you, and that's driverless cars and automated cars and so on. So a couple of headlines really. Where are we with respect of self-driving cars? There's a bit of terminology to get through, but let me start by talking about this. This was a headline in 2016. Statistically, self-driving cars are about to kill someone. What happens next? So not an atypical Guardian headline there. Some more words around that, particularly talking about the Tesla system, which is something you all have heard about. Some terms I've highlighted there: semi-autonomous, autopilot, fully driverless cars, and so on. So there's a lot of information in there. The next one, this was done in 2018. Tesla fatal crash. Autopilot mode sped up before the driver killed. Report finds. So it's an area fraught with risk. And if you look at this final point here, this company in California, there's no end of companies trying to develop this stuff and get stuff out there. But the key point about this final bullet is this thing here, and I'll come back to that a number of times throughout the talk. Humans continue to be the cause of most accidents. So, a theme that will also come out is this idea of managing complexity. Really, autonomous vehicles have to exist in a very complex world. And what I'm going to be talking about is some of the engineering approaches we've adopted to try and manage that complexity. So I'll talk about what I mean by autonomous. I'll talk about how we build autonomous vehicles. I'll pose the question again, is there a problem then? And then finally, I'll come back to leaving it with you. Are you worried still? Or are we going to welcome this stuff when it arrives? So the first stage then is, what do I mean by autonomous? What do we mean by an autonomous system? Well, this picture on the left is kind of one view of it, this notion of a servant that's going to give us everything we need when we want it. Potentially it might anticipate what we want and bring it to us. And from the look of it, you can probably tell it's quite a dated view of these systems. Look at that one there. This was actually taken from an advert about electrification in general. It shows here this family playing dominoes in this car as they're whisked along to their destination. So that's two kind of views of popular views of driverless cars. In robotics in general, here's another one, which tends to be the idea that most of these robots will continue to do what they're designed to do, and that we will only intervene if there's something goes wrong. And that's kind of a hint at where we're at with most robots now, robotic systems and autonomous vehicles. So a little bit more complex then. So let me dig into this notion of what is an autonomous system. And we have to really talk about what autonomy is. And we tend to talk about these four dimensions. We have to know about the operational context of the system, what we're going to do with it, where it's going to operate. We have to know about the level of operator interaction. I'll come back to that point in a second, and it will recur through the talk. And then in terms of what we're endowing this system with, we have to be, how intelligent is it? We can break that down into the reasoning capabilities it has, and then the knowledge it has. What does it know about the world it's operating in order to make decisions? So looking at this graph on the right-hand side here, just to explain it a little bit, on the bottom we've got certainty increasing as I go to the right, and on this side I've got flexibility increasing as I go up the page. So if I look at this system here, some of you might struggle to see it. It's actually the Giotto mission. You may have heard of this a few years ago. This satellite went and rendezvoused with a meteor out in space, orbited around that space, that meteor, and then caused another onboard vehicle to drop onto the surface of the meteor. So that's quite a complex thing to do. But the key point here is that, generally speaking, the level of certainty was quite high. Space travel has matured to the point where we can predict pretty accurately what's going to happen once you get outside Earth's atmosphere. It's fairly stable, fairly predictable, and on the basis of that, we can design our systems quite well to cope with those things. They're pretty much autonomous, those vehicles, because the length of time it takes to send a message to those vehicles and get a response back is so long that you can't do effective human control. So, you can't do teleoperation with those vehicles. Moving a bit further up, you've got this. This is the Docklands Light Railway. Some of you have seen it. There, you've introduced certainty because you don't nip out overnight and stick a new train station on the line. They tend to know when they're coming. The whole system is aware of where they have to stop, how long it takes for them to stop. We've kind of nailed down a lot of the uncertainty there, and we can get these things to behave without a driver on board quite safely, work quite efficiently. Next one up, I don't know if you might have seen these. These are in Milton Keynes. We've got some colleagues from the compound semiconductor catapult. The transport systems catapult operate these puppies here, but they're operating in a relatively benign environment too. Milton Keynes, if you've been there, a lot of pedestrian spaces, a lot of underpasses under roads. So again, you've got a context there that has a lot you've controlled, or you understand the uncertainties involved quite well. Here we get to the kind of car that we're talking about with the Tesla, where the expectation is that it will be able to drive you anywhere you want to go, but it will be required of the driver to maintain attention and keep interrupting the vehicle when it needs to in order to. So kind of like the joke I showed at the beginning, in case of emergency, interrupt what the automation is doing and take control. And then finally up here, generally speaking, when we've got high amounts of uncertainty and we need a lot of flexibility, we still actually put the human being on board our autonomous system. I'll explain why I'm calling that an autonomous system in a second. So a helicopter, a lot of emerging situations where the pilot has to make some quick decisions, the crew on board have to make some quick decisions in order to prosecute missions. So that is why that's positioned up at that end of the graph. So in essence, our intelligence on board the system allows us to cope with the uncertainty and be more flexible. It allows us to address a much more complex mission. It allows us to operate in a much more complex operational context. Finally, I showed you the robot at the beginning serving tea or something to its owner. People, and the media in particular, like to talk about a fully autonomous system. It's my contention that there's no such thing as a fully autonomous system. By definition, they are designed by us to fulfill a particular task. So there is a level of interaction there, however remote or where it happened in the design cycle, but it's doing something for us. It's not autonomous. For me, something that's close to fully autonomous is the autonomous car that when you go to use it on a Sunday, you open the garage and it's taken itself to the beach. That's kind of the autonomy. So, having said all that, I want to talk a little bit about the complexity of things. And this is very topical. It's a cool video, which I'm going to show you in a second. There's a number of videos I've peppered the talk with to keep you all awake. But this is, we had DroneGate back in just before Christmas. This one actually did happen. And this is a picture, a video of what actually happened as a result of that drone appearing. So all these little traces you can see here, like fireflies, each one is an airliner or an aircraft being tracked by the air traffic services. And you can see the kind of flight paths they're taking. But at Gatwick, this drone appeared, and suddenly we've got to do something. So the system has to compensate for this emergent situation. And some of you will have been on jets where they're suddenly told, we're in a holding pattern, our arrival has been delayed by 40 minutes. This is what's happening to a lot of people as a result of this. So the air traffic services will put the jets in these stacks, these holding patterns. They're all separated safely, they're all orbiting round, they're all using fuel, they're all delayed from when they're meant to arrive. And the knock-on effect of that is huge. So again, I'm trying to get across this idea of the complexity of this particular system. So they reopened it, and Hellfire, something else appeared. So they had to do it again. So every single one of those vehicles has got onboard systems, high levels of automation, and support systems to the crews. But the crews are having to work very hard now to sort out these problems, to change where they are in space. The people on board are also trying to manage now, oh, hang on, I've got 300 angry people down the back now that were making a connecting flight or going to a hotel or late for a meeting and so on. I read this week, I think it was EasyJet at that last episode just before Christmas, took a hit of about £15 million because of the delays caused by that. So this is just an advert by the National Air Traffic Service for observing the drone code. So let me move on. Goodness me, that's a bit worrying. If you're on board that aircraft, how do you feel that someone playing in a field has caused all this disruption? Is it a problem? But, and it's a very big but, we don't need to be downhearted. That system, because of the way it's designed, responded very well. All of the procedures that are in place just as a matter of course, that aren't necessarily tailored to that particular incident, responded, kept everyone safe. It was managed. Nobody was hurt. So what I'm going to do now is take you through some of the underlying technology that sort of enables that to happen, which is fundamental to autonomous systems. So how do we build an autonomous vehicle? And I'll start by talking about an airliner, because there's so much automation on there, it's not true. So the two crew there, both of them spend almost all their time managing the underlying systems of that aircraft. They're not necessarily polling, as they say in the trade, moving the stick and flying the aircraft. They're managing the automation that's on board. It's a particular class of control we call human supervisory control. And it's the kind of thing you've got in the Tesla. That's where you are in terms of the technology. I'm going to split it into these three tiers. So this is the kind of technologies we're using in order to achieve automation, high levels of automation, and allow these two to control the aircraft, or supervise the aircraft, I should say. I'm going to start at the bottom here. Automation is kind of the fundamental of achieving high levels of autonomy, and it's actually technology that's been around for a long time. I'm going to talk a little bit more about that, but that's tier one. I'm going to apply it to aircraft, but it's everywhere we look, as I'll show. Then I'm going to talk about system management, which is kind of, there are systems on board which these two are using in order to make things happen. So when they had a diversion and they had to go to a different hold, they were using those systems to create flight paths which they then follow. But the thing about the crew is that these two are the only people with the high level objectives. They're the ones that understand what's going on. They understand the operational objectives, and they are deciding how the system is to respond to meet its overall objectives and keep everyone safe. So, tier one then. This is the unsung hero of engineering. It's generally the module that everyone avoids if it's an option, because it's a bit mathsy. You've all seen it. You're all using it. This on the wall. Except you, Jackie, obviously. The thermostat, very complex piece of kit. You turn it up if you want the temperature to go up, you turn it down. All it's doing is deciding, how much do I need to turn the boiler on to meet the temperature, or do I just keep it off until the house cools down? That's a control loop. They are all over process control in factories, the stuff that make, the places that make all the stuff we use are all controlled by systems that are automated and designed using control engineering. Then finally, we've probably all got one of these in our pockets. And the fundamental electronics and the circuits that are designed inside those things, they're designed using elements of control engineering. And this paper talks about if you pluck a control system a control loop at random anywhere in the world, it's most likely to be on a phone because there are just so many of them around. So it's kind of the unsung hero. It's everywhere. Give you an example that's probably closer to home and more towards a vehicle. We talk about the mathematical models of systems. We make mathematical models of our systems. We have a bunch of tools in a box that allows us to apply a particular design methodology. And then through the magic of feedback, it allows us to achieve some level of automation. So this picture on the right is effectively the cruise control of a car. And what we're designing is this thing. I'll come back to that. But essentially, we control the gas into the engine. More to make it speed up, less to make it slow down. We measure our speed with some sensors, and we compare it with what we've set on the stick inside the cabin. And on the basis of that, an error is created which causes this thing to carry on. It's a closed-loop system. They're everywhere. The controllers themselves, so this box here, takes the error and does something clever to give you an output that drives the system you're talking about. And control is effectively designing these things. What it looks like when you've built it, it can be solid-state electronics. I'm not going to test anyone on these, but basically an electronic circuit that is achieving a particular mathematical operation. It's an integration, which is expressed in these terms, in the runes of this particular discipline. So if I want to know what my output is, I integrate the error, and I've got another set of tools that allows me to express that, and that is a computer algorithm. That basically says my control output this time is the control output I used last time plus a correction which is based on the errors. So you can express that as a computer algorithm. So that's kind of how control works. That's basically fundamentally what it is. Lee was kind enough to mention my PhD work. One of the things I did there was try and build a controller here that through repeated exposure to what it was trying to control, it learned rules in order to be able to do that. So it's a form of machine learning, which is another term you'll hear about. So that's tier one. I'm going to talk now about, build up on that a little bit, just to give you a bit more insight into aircraft control. The principles apply to many, many different autonomous vehicles. They're not confined to what I'm talking about here. Why do we use control in aircraft? Well, for those reasons there. Essentially, when you stuck the wings on it and you put an engine in it, it's not necessarily a stable thing. It might want to just fall out of the sky. So we have to recover that stability, and we do that with a control loop, which I'll talk about in a second. So for stabilization, for configuration, I'll talk about that. And then this thing here, I'll show you a video of later, which is a vertical takeoff and landing jet. And again, we can't achieve that without integrating both the flight control and the engine control in order to achieve vertical landing. For airliners, particularly, the common fact is, and pilots will deny this, the common fact is the autopilot will fly the aircraft better than the pilots and will use less fuel. And that affects the profit of companies, which is why there's a push to do automation in airliners. Some pictures, just thought I'd throw this in for those of you who do a lot of flying. You've probably seen this mostly. This is the kind of the wing out the window. That's what it looks like mostly because it's designed to operate at 36,000 feet or so. There's not a lot of air up there, but it's nice, and they can make the shape nice and slick and achieve the lift they need to cruise at that altitude. However, when you come into land, it's a good idea to slow down. It's easier to get the passengers out, but also you don't need such a long runway. And to do that, you effectively change the shape of the wing. It becomes a different aircraft at that point. And that's what you're seeing when you look out the window. There's also these things here called spoilers, and that's to slow you down on the runway. That's why there's all that noise and rumbling and so on. But the pilot is selecting individual levers possibly, but essentially how far these things go out is pretty much controlled by the automation. So that's what's helping them do that task. The other thing, I mentioned stabilization. The aircraft itself isn't caused to be stable. It can be unstable in that any disturbance when it's in straight and level flight, any disturbance, if indeed you can achieve straight and level flight, any disturbance will cause it to depart and crash effectively. Luckily we don't get to that point. We put one of these things in, which is essentially the control law, or the control loop I showed you before, same idea. We've got some computation. It causes an actuator to move, which drives the control surface. That causes the aircraft to react. We measure what's happening with a particular sensor, in this case a sensor, a gyroscope, and we feed it back and we compare what we wanted. And so it goes round. So that's an auto-stabilizer. Been around for a long, long time. This actually predates some of the theory that we use now and the tools we use now to design them. But this is Sperry at the Paris Air Show in 1914. Sperry company still there doing gyroscopes. But he essentially was in the cockpit waving his hands, look, no hands, I'm not using this. And he got his French assistant to get out on the wing and walk up and down to put a disturbance in to show that the system was stabilizing it. So it's been around a while. This is what it looks like in the sort of design space. There's an actuator model and an expression here that tells me everything I need to know about the dynamics of that. Things in the real world don't react instantaneously. You put a demand in, it takes some time for it to happen. So that's modeled. See, I put the maths up, no one's had enough already. This here is basically the form and numbers there tell me everything I need to know to be able to predict when I move that actuator how the aircraft behaves, how quickly it behaves, how it oscillates, etc., etc. And I measure that and I adjust my gains, and that allows me to stabilize the aircraft. It also allows me to change its characteristics. There's a whole series of lectures on that I won't be going into. So having done that stabilization, you can now wrap other loops around it and do clever things. This is where you start to get into autopilots. So I'm going to show you two videos. This one here is the Vark Harrier. This is a test aircraft where one aircraft is done by fly-by-wire and the rear aircraft is a safety pilot effectively. And this was some work to look at how can you help the pilot out. The pilot in that aircraft, which is basically a Harrier, has got three things to move. The stick, to make it pitch, the throttle, to turn the noise up and down, or the thrust up and down, and the other thing is the nozzle lever. That's which way is the thrust pointing. So moving a lever and it points down or all the way back. And if it's all the way back, it's acting like a normal aeroplane, but they have to get from that situation to hovering by moving the nozzle round. So three things to move, two arms to do it with. The original one-arm paper hanger to make this happen. So some of the work I was doing back in the day was a part of a vast team, and I can take no credit for this at all. I was just one of many people doing various things, was to try and design the control law to allow them to do it with just two hands. Also in this is the notion that and I'll point it out in the video, is that the pilot is away from the ship, so a shipborne landing, it's away from the ship, it's operating, it's doing whatever it has to do, but then has to come back. So it has to get back to the ship and get to the position where it can operate these things. So let's run the tape. Sorry, Kinetic promotional video. There's one bit I want to stop and explain. So this is the thing that was designed. Oh. I missed it. But that was the route the thing is flying to get the aircraft back. What you're seeing here is the view through the front of the aircraft. It's very difficult to make out, and apologies for the poor video, but there are green lines on there. That's effectively the head-up display. That's giving indications to the pilot what the system is doing, what the automation is doing to allow him to carry out the mission. And that other shot there is effectively a shot of his hands in his lap. And he's wearing white flying gloves, because pilots always do, and essentially they're not moving. This is all automated. So there you can see the superstructure of the vehicle. So you notice we put that comment in. So the next video, effectively, defence research, basically this is what you're trying to achieve. Having done that concept demonstrator I've just shown you on the tape, this happened earlier last year, 2018. This is the Joint Strike Fighter, the F-35 Lightning II. This now, the pilot in that has got a high level of automation. He's only using his two hands to move two levers, and all the rest is automated. So effectively achieving the same thing, but much, much easier. The pressure on doing that is that if you're wrestling to fly the vehicle, in the parlance, you're not operating the vehicle. You're just trying to position it. So what you're trying to do is reduce the amount of effort needed to move the vehicle and allow the human to do what they're good at, and that's pattern matching and decision making and goal setting and so on. I can probably move on, but you get the idea. But that's quite good for us, because it's not often that you can get something from the research program in defense research into a product, especially when the product is American. So we were feeling quite good about ourselves when we did that. So, and I've put this in, it's not necessarily following the same flow, but it is a good video, so I thought I'd put it in. Rockets are actually autonomous vehicles, as I said. I know, Kath, you get a bit, crush on Elon Musk. Yeah. This is the Falcon heavy lift. So this is I'm going to show you a video in a second, but just to explain what's happening, there's a rocket. This is my visual aid. This is a rocket, and what you're essentially trying to do with a rocket is balance it on the nozzles here, the thrust coming out of the nozzles here. So you're doing this. It's a classic inverted pendulum. This is the kind of thing we can get students to do as part of their coursework, is design something that allows us to balance on that. We can move the nozzles a little bit to get that direction, only a little bit, because after a while you just can't recover it again. So what they do at the top is you can see that there are little puffers there. So they're a reaction control system, and that basically just gets it moving, especially when it's outside the atmosphere, because there's nothing else to do that. And then finally, it's probably not that clear, but there's like a thing that looks like a manhole cover on the top. There's 4 of them. They're effectively drag things to give it stability as it's coming back. And what you're trying to do is you launch it that way. It goes out the atmosphere. It's going that way, but you want to bring it back over there. The reason we're doing this is if we can reuse these bits, it becomes commercially viable to do this with space travel. So what it does, it goes out, the puffers react, it turns, comes back this way a bit with the thrust, and it goes back again to come through the atmosphere and land where we want it to. So it's quite a big deal, it's quite complex. The equations at the top there are part of the problem. They're basically because, unfortunately, the Earth's spinning, so your landing spot is moving. So when it comes back, you've got to compensate for that if you want to hit it. So those equations govern that. The other thing is that, and this makes it difficult for control people, is that because you're burning all this fuel, the center of gravity of this thing, the dynamic reaction changes throughout the flight. So your system has to be able to compensate for that in order to point it in the right direction. So let me run the video. You can see it's quite a big deal, but how overjoyed these people are when it all works. There's a lot of commentary about various things, but I won't go into it. But essentially, this is the launch phase, as you can see. Various bits of instrumentations. When it gets to the fastest it can go, then you see the boosters pop off. I've edited the video a bit to take out the nonsense about releasing the car. But you can see now they turn back over to come back downrange to where you want to land. And now they need to turn again to come back through the atmosphere. There's a mixture of simulation and real footage here. I'm convinced it happened. So there you can see the nozzles vectoring, these things dropping like a stone. The stand comes down, they have to then get the thrust out in order to arrest that descent. So that was a good day at the office for that team. So it's my contention there that I think most of that was automated. So because of the dynamics of the thing, because of the problems with communicating with something at that point, I don't believe there was any human interaction with it in order to make it happen. So that's quite there's a reference on there earlier, which is the team, I believe, designed the guidance law for that particular system. So I've talked there about aircraft with humans on board. Then we ended up with that rocket, which clearly violates the definition of what is a drone, what is a UAV. It's when your missile comes back, is generally how we used to term them. But in this instance, a rocket, which is a new genre of rocket, comes back and we can reuse some of it. So having done a lot of work on aircraft, the logical extension, for various reasons which I'll go into in a second, was to essentially see what benefits there were by taking the human out of the system, out of the driving of the system. And I'll come back to that. We've seen, the police are using these things now. Dull, dirty, and dangerous. Dirty missions. That, if you'd recognise it, was Chernobyl. Remember the core cracking, all the leakage of radioactive material and so on. And these poor dudes in here, helicopter pilots, taking concrete to drop on the core to try and stop it leaking. I think every single one of them died from radioactivity poisoning. So it was an ideal mission for something that's not got a human on board. Amazon are threatening to do this. Again, from what I said right at the beginning, operational context. Are they really going to do that in Cardiff? I can see them doing it out in the sticks in remote farms and so on, but not in Cardiff. And then, when we start to want to have really sort of futuristic, stealthy shapes, we take off some of the fundamental control surfaces. We have to recover that. They're on there for a reason, so we have to recover that means of control some way. And again, control can do that for us. Once the vehicle is unmanned, we can use it in places that we wouldn't want to put human beings. So, the use case that motivated the sort of most of my work in the sort of early to late 2000s was the idea that we wanted to understand how to control these things, how to make them more intelligent. So this was to meet an MOD requirement, which was to allow us to use the unmanned elements to do what they call force multiplication, to add capability to our existing forces. To do that using unmanned air vehicles, we did some early work where we were thinking about how can we control them from another aircraft. We had other aircraft, we can't just forget them. Do we get anything by allowing the pilot in that vehicle to control the unmanned vehicle? What it became apparent was that we had to establish a partnership between the intelligence on board the vehicle and the human decision maker that was kind of owning the capability, was making all the key decisions, making sure we understood the objectives of the mission. And it meant that in order for that to happen, if you make a decision in this aircraft and you've got this aircraft that you're trying to control, you're linked with a Wi-Fi link, effectively a data link, and you don't have unlimited bandwidth. So you've got to reduce the amount of messages you send. That makes the unmanned system have to be very intelligent in order to cope with the uncertainties that I've talked about all along. So my role in this was effectively assembling a team of robotics engineers, people who've done machine learning, people who could build agent-based systems, human factors people, and system engineers to try and bring this multidisciplinary team together to design those systems in order to trial them and work out if there was merit. So before I go on to that, keeping an eye on the time, I'm going to have to speed up a bit, but essentially this is right at the heart of a key element of humans interacting with machines. This was some work by a guy called Rasmussen, the reference is at the bottom, one of many references of his. But essentially he was trying to construct a model of what was happening when people working in things like the nuclear industry, how were they treating things going wrong in a nuclear plant? How were they interacting with the plant in order to make sure that it continued to operate safely and so on? So he postulated this idea of human cognition. And if I'll give you a quick example to run through this. He had these three levels. And basically this matches the way we do things. So skills, rules and knowledge. Skills, think about driving your car. When you learn to drive the car, the thing that gives you a lot of trouble is when and how to change gear. When you've been driving for a while, you no longer think about that, you just do it. It's automatic. So what you're doing then is you're using rules, which again are largely internalized. Approaching a junction, I need to change down, you just do it. It's transparent. However, if you reach a new situation, which you haven't been in before, so let's say you skid for the first time on ice, you then use your existing knowledge about friction, about momentum, about how a car operates and so on, to construct new rules to try and come out of that safely. Or not, in some cases. But essentially that's how we kind of work things through. So that's sort of a simple introduction to Rasmussen's work. If I jump back to what I was talking about right at the beginning, automation, system management, the pilots in the cockpit, and then the pilots themselves having these high-level objectives. If I put Rasmussen's stuff next to it, it hints at there being a nice complementarity there that we can exploit. And really that's what the research was about, is trying to understand what's the mix. And generally speaking, these things we leave to the machine, because we're quite good at making those, as I hope I've demonstrated. Some of the rules as well, most of the rules in fact we can encapsulate in our management systems in order to help us do this. But where we get where it gets a bit more difficult is this knowledge level. And if we combine those two things, generally we're trying to blend what the human's doing and what the system is doing, and do that in a way that makes sense to both. And there are some problems, I'll come back to them. So having done that, we did some work on what we'd done, taking the automation, and this was kind of the, not quite the end of the program, but we proved here, on board here is a laboratory, I'll come back to that, and this is where the controller of the system is sitting. So there's two cockpits on there, but the guy we're talking about is sat in the front. And essentially what we did here is we said that airliner is a UAV. We connected our software to the autopilot. And then on board that airliner, we also had 3 simulated UAVs. So the data link that connected the airliner to the guy sat here, on his displays, he saw 4 dots out there. So he was controlling 4 UAVs. And with the intelligence we put on board the vehicle, we were able to allow departure from Boscombe Down, orbit over here. The fighter aircraft orbited over here, out of harm's way. And then the surrogate UAV plus the 3 simulated UAVs went and did a mission over Dartmoor. And then they were recovered by the pilot here. And the thing we'd done is put enough intelligence in those UAVs that the level of interaction between the pilot and the system was low enough that someone who's fairly busy anyway could cope. So that was kind of a culmination. We got some plaudits from this guy, which was quite nice. Bit of a shout out. So that finished that bit. The next stage was to take and apply that software in a slightly different setting for this stealthy UAV. Horrible video, BAE Systems. But you'll see the kind of thing I'm talking about. I'll cut it short rather than go to the end. But this is basically a stealthy aircraft. This is a strategic thing because it enables the UK to maintain its ability to design these kind of things. And this is the trouble if you buy something like the F-35 from the Americans. You kind of forfeit the abilities to then continue to be able to build them. So quite a big beast, built up in BAE Systems Wharton near Preston. It was loaded into the back of this vehicle, taken down to the outback, quite literally. Undisclosed test site, sorry, I think we've moved on a bit since they published that. But then, so the team I was leading, we were lucky enough to get the contract to put some of our software on this thing. I'm gonna cut it short there, but you get the idea. So then that brings me back to, I've shown you all this technology and I've shown you how it kind of relates to things. Is there a problem? That interface between the operator and the machine, the automation, what is the issue there? Well, there's a number of issues, but I picked out a couple. I'll say at the beginning, I'm going to be talking about plane crashes. Plane travel is still the safest way to travel, but I'm going to be talking about plane crashes. For those of you who do a lot of travel. So this is the autopilot in the A320. There's that nice little switch there, and the pilot, depending on which way they've thrown that switch, is either with one of these knobs setting this thing called flight path angle or vertical speed. And whatever is set in those two there dictates what those numbers mean. So in this incident, the pilot wanted flight path angle to get, that would mean 3.3 degrees to descend into the airport. But what they'd actually got confused about was they'd set vertical speed. Those numbers now mean 3,300 feet per minute. That's about 10 degrees. And as a result, they descended into the mountainside and crashed. So that's a very simple thing. It's an interface design, and this thing, mode confusion, they for whatever reason didn't know what mode they were in, and that caused that error. Next one. It's very safe. So it is very safe to fly. This aircraft is coming to land straight into this airport. This is in South America. They're given clearance to do that. They set these symbols here represent nav aids, as they're called. So they're just beacons that you tune into, and they give you information into your automation to allow you to sort your flight path out. They were told to set in Worrisome, which just happened to be letter R, in their flight management system, stored against R was this place, Romeo. And it had exactly the same frequency as the other one. So the result was they dialed it into the flight management system, expecting it all to work nicely. It then turned away from the airfield and they thought, oh, hang on, what's going on? We were expecting a straight-in approach. They looked at what was going wrong. They then took control of the automation to turn it back to come towards the airport, not realizing then that they were on the other side of a very tall mountain, crashed into the side of it. So, very, very simple errors that cause these kind of problems. Here's another one, this final one, I promise. This one is the Air France Flight 447. You may remember this one. Aircraft disappeared over the Atlantic. What's happened? And then eventually they found the aircraft, they retrieved the flight recorders, and this little expression here, taken from this reference, is essentially that last conversation, and that's quite harrowing, I think. So they crashed into the sea. What caused it was essentially the junior pilot was left in command, which is quite ordinary, quite normal. But in his training, he hadn't done enough familiarization with the symptoms of a stall. So that's when the aircraft is doing this kind of thing, and the flow over the wings tends to spill off, and that causes it to lose lift, and it sort of wallows out of the sky like that. It's a stall. That's what was happening. There was a couple of other mitigating things that were contributing to this, but essentially that was what was happening. This aircraft has side sticks, so you can't see from where the stick position is what the stick is demanding. So the senior pilot comes back in, he looks across, what's happening, comes up with the wrong diagnosis, and the thing just stalls straight into the sea, disappears. So again, a relatively simple thing, but that talks about how we train people and what we do when we rely too much on our technology. It gives us an issue. So I am coming towards the end now. My timekeeper's keep looking at his watch. But so human supervisory control. The thing I've been talking through all of these things is essentially that the only person that's looking after the mission, the goals of what you're trying to achieve, is the human. The machine knows nothing about it. The automation function knows nothing about it. Generally, for machine automation, and these are all generalizations because you can always point at specific cases where they're not, where it's been addressed. But generally speaking, it doesn't explain its operation well. It's an interface thing. It's doing something, but it's not often easy to see what is it doing. There's that sort of gulf of understanding. It's brittle. It's designed to operate in a perfect world. No, that's not true. Designed to operate in a way in the bounds that we expect at design time. And whilst they can be quite wide, you often reach bits where you no longer are operating in the regime you designed it for. That's brittleness. And then literalism. It does exactly what you've designed it to do. And no amount of wishing will change that. It just does it. So those are problems with the technology. I'm going to jump back now out to the ground thing because I'm going to wrap it up. But essentially, this is an Audi system. So remember right at the beginning I talked about operational context. Audi are going the route of saying this is a traffic jam autopilot. You would engage it when you're in a long train of traffic. And if you think about that, it's quite predictable, isn't it? It's just you're just moving along. Everyone stays in their lanes for the most part. But essentially, it's predictable. It's limited to speed, and you're just looking out the window, and it's driving you there. I must confess to having used cruise control to do something similar. It kind of lends itself to that. Tesla's autopilot, a bit different. I've shown you some references about that. That's what this is. It's trying to do something more ambitious, and it's relying entirely on the human driver to remain vigilant to do that. And there's already been one death where that hasn't been the case. Generally, what you're trying to do, a human being, generally speaking, has a sweet spot in terms of workload. Too little, and your performance drops off. Too much, and it drops off. There's a sweet spot in the middle. That's what you're trying to do with the interface. When you whip out your Sudoku or whatever, when you're driving, you've dropped right off. You're no longer engaged with what's happening. I'll come back to that. And then finally, I just wanted to put this in because I thought it was intriguing. This is a thing called a cobot, and there's going to be a lot more of this. It's humans working very closely with robots, cooperative robotics. And the idea is here that rather than have two pilots, you just strap this thing to the other seat, and it knows how to fly. So it does all the things the co-pilot does normally, pressing buttons and so on. I don't think it's anticipated that they'll be doing that on your EasyJet flight. I think it's more that when you've got a jet in the wrong place, because some idiot with his drone has caused you to divert, then it's a cheaper way of getting it back to where it needs to be. Engagement is the thing. I'm just going to run this video a little bit here. If you can see it, this is young people being monitored in their cars and how much attention they lose through various reasons. I'm not going to let it run too long, but essentially this car coming, spin. So it doesn't take much to lose attention in that kind of operating environment, which we've all used every day. There's a whole range of them there. So in low workload motion situations, we need to be able to engage people's interest. Another point I'd make, I am getting there, Sean, I'm sorry. So here we got a recent test drive of a Tesla. This guy, again from The Guardian, what's it like to drive a Tesla? And he makes a number of points here. This one I quite like. Although it can work on some residential lane roads, it's highly dependent on the quality of the road markings. Just map that to Cardiff streets. But it does improve over time, so they're allowing it to learn over time. But that's still a problem for us. We still don't generally know what it's learned, and we can't prove it's learned what we want it to learn. So Autopilot is used to improve the system, and then it's pushed out to all the drivers via the software updates. Now, has anyone ever got an update on their phone, and then suddenly the phone doesn't work? So this is a real issue, and I just hope that they're talking about that as well. Other things. We have to have ways of sensing where we are inside our vehicle. This is a picture on the back of that people mover. There are pictures painted there of people on bikes. This vision system has picked up that there are bikes with people on them. So that's affecting its decision making now. It believes that there's something there and it would take appropriate actions. So you get these emergent situations where it's not clear how they're going to evolve over time because it changes second by second. So it's quite complex. So we get to the end. Should we welcome them or be worried? It's not as bad as I perhaps painted it out. If you look, there's a European initiative going on. I'm not going to go into the detail, but if I just point out, this is an architecture that's being proposed for smart self-driving cars. It has an element of automation, tier 1 as I've called it. It has this element of system management, and remember it's looking across the power management of that system. It's looking across the environmental conditions inside the vehicle. It's looking across the sensors, the computing elements, and so on. So it's looking across all of those things. It has an interface to the driver because the driver must remain engaged. So HMI is being looked at there, human-machine interface. And then finally, something I haven't talked about here, but is critical to self-driving cars, is what I'm calling tier 0. That's the thing that measures what the world is doing outside. I talked right at the beginning about knowledge. That's where we get our knowledge. Onboard data, the model of the world that we have on board, how that is added to by connecting to other vehicles and other systems that are out there in the infrastructure, and then the things we measure in real time using our various sensors. So that's kind of what's going on. It's all about managing complexity. It is complex. So what we have to do is really understand, in order to operate in this complex environment, identify and design that right level of human-machine interaction. I mentioned the sweet spot. That's that kind of thing. We have to identify and design the right approach to solve each granular problem. I don't believe there is a silver bullet here that fixes all this in terms of the algorithms that make the decisions. What I believe is it's a vast collection of different approaches to solve different granular problems. So what we've got then is a problem of how do we glue it all together in order to make the decisions properly. So software architecture is a big thing to make these things work. Implementing the software, I'll come back to. But then there's that picture I showed you. How do we perceive that what we're seeing out there is real, and how do we make sure that the decisions we make are correct? And then finally, guarantee system safety. So, this is my last slide. So, should we be worried? Am I worried? I think it's too early to say. In time-honoured fashion of researchers, I think we need to do some more research. Basically, the complexity of the operating context with regard to autonomous vehicles in general, but particularly with cars, I don't think we'll be able to operate autonomously in our nuanced world for some time yet. I've seen forecasts for 2030. I'd add 10 on that, personally. Here, at the moment, we still need to allow we kind of sweep up the slack with the human operator. They have to do that key decision making. And I think because of that, we'll still have an initial deployment that's quite limited, operating in segregated lanes maybe, or in parts of the motorway, that kind of thing. And then because we've got more and more software that I've talked about kludged together, and we have to organize that, we have to ensure that A, it's going to correctly function. So that gives a lot of the burden on the AI stuff we decide we're going to use. Can we prove it's doing what we said we want it to do? It's got to operate securely. It can't be Windows 10. It can't crash when you don't want it to. And there are many, many certification issues to be solved. Flying, generally speaking, you have to prove that there will be less than one catastrophic failure in 1 billion flying hours. That's the limits we operate software to with it. Well, the whole safety case within the air world. Proving that is actually quite difficult. It takes a long time to gather that evidence. And there is research going on with methods to try and mathematically prove software code and so on, but we're some way off being able to do that. It's not all bad. We've got some time to go, but I'm finished. Thank you very much.